Good morning, students. Last two lectures we have seen different type of reactors used to design the single reactor system. In that we have seen equal size mixed flow reactors and their behaviors. Then we also seen unequal size mixed flow reactors and its behavior. Today we are going to see if we have different type of reactors like PFR and mixed flow reactor, and if we attach that in series, then what is going to happen. So here we have one small mixed flow reactor, then we have a plug flow reactor, and then again we have a large mixed flow reactor. Number of times in the industries we have to use a combination of mixed flow reactor and plug flow reactor just to increase the conversion at lowest or minimum possible volume. So here you can see we have three reactors in series. One is a small mixed flow reactor, then we have a plug flow reactor, and then we have a large mixed flow reactor. If we have these type of systems, then we must know how to find the size of each reactors. Now for that I have written the performance equations. If you see this performance equation is of mixed flow reactor 1. Then if you see this performance equation, then it is the performance equation of this plug flow reactor. And if you see this performance equation, then this performance equation is of large mixed flow reactor. So I have written the performance equation of each reactors. In mixed flow reactor 1, the conversion will increase from x0 to x1. Then in the plug flow reactor, the conversion will increase from x1 to x2, and then in mixed flow reactor, the conversion will increase from x2 to x3. So volume V1 is the volume required for mixed flow reactor 1. Volume V2 is the volume required for plug flow reactor 2, and V3 is the volume required for mixed flow reactor 3. So if I want the conversion from x0 to x3, then I want to find out what will be the total area required for all this reactor system. So here you can see the diagram. As you know, this is 1 upon minus RA versus conversion, and the graph will be like this. The rate of reaction will increase with respect to rate of reaction decrease with respect to conversion. So 1 upon minus RA will increase with respect to conversion. This shaded portion represent plug mixed flow reactor 1. This dotted portion represent the plug flow reactor 2, and this larger shaded portion represent the volume required for mixed flow reactor 3. So if I want to find out the total volume required, I have to make the addition of area of this rectangle, that is the area required for mixed flow reactor 1, area under the curve for a plug flow reactor because there is an integration sign here, and then this rectangle represent the area of mixed flow reactor third. So this addition of V1, V2 and V3 or area addition will give the total volume required for the conversion from 0 to x3. So if you are having a different reactors in a series, we can find out the total volume required with the help of this geometrical diagram. So for that we are going to see now one problem, how to find the best system for our reaction. So here you can see at present the elementary liquid phase reaction A plus B gives R plus S. Now here elementary, as you know, elementary means order directly correspond to stoichiometry. So order of A is 1, order of B is 1. So this is a second order reaction. Then it's a liquid phase means what? Constant density system takes place in a plug flow reactor using equimolar concentrations of A and B. So we are having same quantities of A and B. The conversion is 96% and initial concentration of A and B is 1 mole per liter. Now if a mixed flow reactor 10 times as large as plug flow reactor is hooked up in series with the existing unit, which unit should come first and by what fraction production will be increased for that setup. So here we have a problem where we have already a plug flow reactor where we are getting 96% conversion. Now I want to add one more mixed flow reactor in series with a plug flow reactor. Question is whether plug flow reactor should be followed by mixed flow reactor or mixed flow reactor should be followed by plug flow reactor. So this problem we are going to solve. So we have a reaction A plus B gives R plus S with equimolar quantities of A and B. As this is an elementary reaction, I have already explained. For elementary reaction, order with respect to A is 1, order with respect to B is 1. So here you can see the rate of reaction minus R is KCA square, second order system. If you write in terms of conversion, then I can write KCA0 square 1 minus XA square. For liquid phase system, epsilon A is equal to 0. That you are already familiar. Now given CA0 is equal to 1 and XA is equal to 0.96. If we have that, then the performance equation of plug flow reactor I can write, as we already studied the performance equation of plug flow reactor, I can write tau is equal to V by V naught CA0 0 to XA dXA upon minus RA. CA0 remains as it is. For minus RA, I have written K CA0 square 1 minus XA square. If you simplify this equation, then if you simplify these integrations, then we will get tau is equal to 1 by CA0 K 1 upon X 1 minus XA with respect to interval 0 to XA. Simplifying further, you will get this, and here I have substituted the value of XA is equal to 0.96. If you substitute that, you will get the value of V. Here V is the volume of plug flow reactor, that is 24 V naught by K. So this is the volume of plug flow reactor we are going to get. Now we already know that we are going to add one mixed flow reactor which is having a volume 10 times that of plug flow reactor. So I can write Vm is equal to 10 Vp, that is 240 V naught by K. Now consider case 1, PFR followed by CSTR. So we are having a one PFR which is the original PFR where 96% conversion we are getting, that is X1 is equal to 96%. This is followed by another mixed flow reactor where Vm is 10 times Vp. Now if you have that, obviously the conversion will increase. So my job is to find out value of X2, how much conversion I am going to get with the system. So in the PFR conversion actually is 96%, therefore I can write X1 is equal to 96 because this PFR is same as that of previous PFR. Now for CSTR I can write the performance equation V0 by V0 C is equal to C0 X2 minus X1 upon minus R. I have written the performance equation of this mixed flow reactor. So here X2 minus X1 upon minus R. If I substitute the values, here you can see rate of reaction is KC0 square 1 minus X2 square because this is a second order reaction. Here I have written X2 because the conversion in the mixed flow reactor is X2. So I have written minus R is equal to KC0 square 1 minus X2 square. If you simplify this, you will get this equation, and if you simplify this equation, you will get the value of X2 0.989, means 98.9% conversion you are going to get if the PFR is followed by CSTR. Now we are going to see another system. Suppose first of all I am going to use CSTR and then it is followed by PFR, then I will have this type of reaction. So here I have MFR where Vm is the volume of mixed flow reactor and it is followed by PFR. Now here X1 cannot be 96 because this is not plug flow reactor, this is a mixed flow reactor. So I have to find first of all X1 and then I have to find the value of X2. So for that I can write the performance equation of CSTR. Now this CSTR is 1, so you can see the performance equation V by A naught C0 into X1 minus X0. X0 is 0, so nothing is written here, and then minus R is now here minus RA 1 because I am writing the performance equation of first reactor where the conversion here will be X1. By mistake here it is X2 written, but it is X1. So I will have the performance equation K C0 square 1 minus X1 square. If you substitute the values, you will get this, and again if you substitute you will get this. Now this is a equation. If I solve, I will get the value of X1 is 0.9375. This is the conversion takes place in mixed flow reactor, which is X1. Now based on X1 I am going to find the value of X2. So to find the value of X2 I can write the performance equation of PFR. Now PFR is a second reactor, so here you can see the performance equation of PFR is same. Only here we will have x0 to x2 because the conversion taking place from x1 to x2. So for that I want to find the size of fixed plug flow reactor. If you simplify further, x1 I have substituted 0.9375. So if you solve this, you will get this. Again, if you simplify further, then you will get the value of x2 finally. So here x2, if you see, I am getting 0.975. So final conversion will be 97.5%, and in the first we are getting 98.9%. So comparing PFR followed by CSTR and CSTR followed by PFR, obviously the best conversion we are going to get in PFR followed by CSTR. So we are going to decide that we are going to use PFR as a first reactor and CSTR as second reactor, so that we can get maximum conversion. Thank you.